All right, so we've covered chapter 4. Now we're going to go back and kind of start at the beginning with chapter 1. Chapter 1 is kind of how to describe and look at data, if you will. So section 1.1 is focusing on categorical data, and then section 1.2 and 3 will focus on numerical data. But first of all, let's go back, step back, and talk about some definitions. Individuals and variables, we've kind of talked about this already, but an individual is an object described in a set of data. Individuals can be people, animals, or things. We may be looking at our class data. I can open this. Whoa, this is really small. So if you look at the survey that's on your calculator, every row is an individual. So the first individual was 14 years old. They were a female. Their shoe size was 7. And you can go across. So each row was an individual or subject. Variable is an attribute that can take different values for different individuals. So then each column is a variable. Each question we asked, gender. There was, female, male. I think there was an other option also. There are two types of variables, categorical variables, sometimes called quantitative, and qualitative, sorry. Qualitative. I don't like qualitative. And quantitative, also known as numerical. As far as I'm concerned, you're responsible for this one, and this one. I don't use qualitative very often, but if you ever hear it. Categorical assigns labels that place each individual in a particular group. For example, when I asked your gender, you either identified as female, male, or other. And then quantitative takes on number values, basically counts or measures. How old are you? That was a measure of how many years you've been alive. Hair length, that's a measure of how long your hair is, etc. Do we ever use numbers to describe a categorical variable? So we'll give an example. So we discussed this in class, and I challenged kids to come up with it. The answer is yes. A good one I like is zip code. My zip code is 77381. Well, that's a number, obviously, so you might think it's numerical, but it's not really a measure or a count. It's not a distance from some central location or anything like that. It's just a number label given to a certain geographical region in the country, I guess. You could also argue things like student ID, phone numbers, social security numbers. Now, a lot of these are unique numbers. Like student ID is unique, and social security number would be unique. They're numbers that are not measures. Rather, they're kind of like identifiers. Even phone number, whereas zip code is more like a categorical variable where everyone that has the same zip code is in the same area. These can be broken down a lot more specifically, all these variables, and numerical variables can be broken down into several categories as well. But so I would say zip code is categorical, not numerical. The same variable can be measured using either categories or numbers. For example, soft drink sizes. So you could record soft drink sizes as a category and talking about small, medium, large, extra large, venti, whatever you guys, or numerically. Numerically, you might record 12-ounce drink, 15.5-ounce drink. You could actually measure the quantities. We did have discuss some advantages and disadvantages of each. We do have an advantage when we're working with numerical data that we can calculate averages. Standard deviation we haven't talked at all about, but you can do more measures on numerical data, whereas here you can't really talk about averages as much. There are some advantages to categorical data. When I gave this survey, one of the questions I asked was something about text messages, or even really anything that was open-ended. Text messages, I left it as open-ended. You could put it as many texts as you wanted. Some people would say 30 plus. Well, what was I supposed to do with 30 plus? I wanted you to give me a number, or 40 to 60, or not that many, a lot, things like that. If I would have done categories, if I would have said you send 10 or less, or 11 to 30, or 31 to 50, something like that. If I would put them in categories, it would have forced people to answer in one of those categories and not allowed them to give me answers that were not useful. Okay. Um, yeah. So they're different. The other thing I want to comment on is, can you switch between them? If you have categorical information, can you make it numerical? Usually, I would say you maybe can't, but I guess if you're talking about McDonald's and you're talking about what size people order, small, medium, or large, if all of your smalls are the same size and all of your larges are the same size, we could convert those all into like 10 ounces and all of these to like 16 ounces or whatever, right? But if you start getting different restaurants and different, gas stations, then a small might not always be this. So in general, it's very hard to go from categorical to numerical, but you can fairly consistently and easily go from numerical to categorical. You can kind of classify whatever sets of numbers you want into whatever categories you want, So certainly advantages of numerical and categorical, back and forth. Distribution. So this is probably the most important word we're going to be talking about all year long. When we get a data set, collect any data, we're going to talk about how that data is distributed. Describe the distribution. The distribution tells us what values the variable takes on and how often it takes on those values. So how do we describe the distribution? Well, here's the heights of high school, sample of high school students at our school. You can see that, I guess you could say, well, 74, there were five kids that were 74 inches tall. And there were 4 kids that were 71 inches tall. So that's one way, I guess, to describe what values it takes on and how often, but that's not very summative. It's not a very good summary. It's not quick, it's not easy, it's a lot of numbers, and it doesn't really give you a picture. A graph, a dot plot like this is really a fantastic way to display and to show somebody a distribution, because I can see where there were common values, where there weren't any. I can see basically the entire data set in one quick little glance at a picture. So this is a fantastic way to display a distribution. We're going to be talking about how to describe a distribution. This is a numerical variable. In this chapter, though, we're going to be talking about categorical, and then we'll revisit stuff like this height graph down the road. So how do we describe the distribution of a categorical variable? I got 5 different things here. We have a data table, a frequency table, a relative frequency table, bar graph, and a pie chart. So data table is your raw data. So that's not very helpful. That's just, on our calculator, there's my data table. Not very easy to view the data at all. Frequency tables and relative frequency tables. Frequency is synonymous with counts. Frequency is counts, and relative frequency are percentages. So just make sure you understand those 2 words. So if we're looking at hair color of every individual, instead of a raw table saying first individual's hair was brown, second was blonde, third was brown, we could summarize it in a frequency table. 32 people had black hair, 31 people had blonde hair, etc. And then if we had a total of 154, you could take 32 divided by 154 to get this 20.8%. So this would be a relative frequency table. In class, we talked about pros and cons of each. I'm not going to get too much. Well, there's one very nice thing. Percentages are kind of nice. They're easier to compare, I guess. One thing about when you're looking at percentages is if you don't know the total counts, then that doesn't give you a sense of how many people there were. One of the drawbacks of counts is, let's say you had hair colors of guys and hair colors of girls, and for some reason you sampled 100 guys and you sampled 1,000 girls. It'd be hard to compare counts because this might be, let's make it an ugly number, 2,768, 3 girls. So when we're looking at black, if black hair was 30 people here and it was 623 people there, it's hard to compare those numbers. If you report them as percentages, then it's very easy to compare these percentages because you just see if they're the same or which one's higher. Bar graph, you guys know what a bar graph is. This is a frequency bar graph. I could put percentages there also, or relative frequency. You can move these categories around any order you want, and this is a pie chart. Okay? So these are good graphical displays that summarize the numbers we're seeing, the summary numbers we see in this table here. Discuss the pros and cons of each and which ones do you like better. I guess one thing I mentioned in class was bar graphs versus pie charts. Which ones do you like better? Most kids say pie charts. I mean, I love me a good pie chart also. And when you guys do your project, I'm going to encourage you to use a pie chart because people really like to see pie charts. But statisticians don't like it as much. Like if I see red here, it's very hard for me to estimate either how many people had read or what percentage had read. I mean, I know it's less than 15% or 25%. Probably, I mean, you can estimate it. It's a little easier to estimate over here because you can kind of just project it over and say, oh, that's 9% or whatever. So statisticians kind of like bar graphs a little better than pie charts because they're sometimes easier to read and get information from. But whatever. If we put the percentages here, that makes that kind of obsolete too. AP testing advice. When making graphical displays on the exam, you must label and scale all axes and maybe include a title. You should include a title. Actually, they're not as picky about titles as they are labels and scales, but you don't want to take a chance at losing points for anything. What's wrong with the following graph? 95 channels on DirecTV, 81 channels on Dish Network, and 56 channels on cable. So if you scale this to 95 and you project, I guess I should say 95 here, I project this over, not so sure that that's scaled properly. This is 81, wouldn't 90 kind of be like about right there? So it looks like they're stretching this graph out to make it look like this is much bigger than these. And this is supposed to be 56. Yeah, I don't know. The other thing is that they're making this much, much wider than these two. So this area here is much larger percent-wise than these two areas here. Much larger percent-wise than the number of channels, for example. This is a violation of the area principle. The area principle says that the ratio of the areas should be the same as the ratios of the numbers in the data set. And if you do something like this, when people glance at it, they say, man, look at DirecTV, huge set of channels, and these ones are really, really small. When in reality, this is only, 14 more channels out of 100, out of 80. This happened in my school when I was teaching in Minnesota. We had an English, like standardized testing and a math. And the English did better than the math. English got their pass rate was like 56%, and the math pass rate was 51%. So they put this graph in our meeting. Percents. So they said these are the English passing rates, and this is the math passing rate. And then they talked about how we need to work in math because our math scores are so low. I'm not saying our math scores aren't lower. They are lower. But are they 6 times lower? No. This is another violation of that area principle. If you were to do this scaled properly, this is 50, then English is like here, math is like here. It's not it's a difference, but it's not that big of a difference, perhaps. I don't know. it was a deceiving graph. It was a misleading graph, and I talked to him about it.